Modern medical implants present a serious physical contradiction. They provide the internal support needed to save limbs and lives, but because they are made of permanent metals like titanium, patients often have to be sliced back open to remove the hardware once bones heal. Biomedical engineers sought a natural exit strategy. They looked to magnesium, a metal that safely dissolves inside the human body over time, entirely removing the need for a second extraction surgery. Inventors Siti Nurbaya Muhammad Badari and Asmawi Sanuddin at University Malaysia Perlis focused their research on making this temporary material viable. But there is a strict biological barrier preventing its use. In the medical engineering field, it is known as the Magnesium Standard Failure. This animated diagram shows a standard metallic pin securing a fractured bone. When untreated magnesium is exposed to human bodily fluids, it degrades rapidly. It dissolves before the bone fragments can naturally fuse together. As the metal thins and gives way, the internal support structure collapses under the patient's body weight. Until engineers could slow down this rapid decay, magnesium remained an unusable material trapped behind its own chemistry. To isolate the cause of this decay, the UniMap team had to examine the physical environment at a microscopic level. The exact mechanism destroying the implants is called tribocorrosion. It is a highly destructive process driven by two separate physical forces feeding off each other. The first force is friction. Every time a patient breathes or takes a step, surrounding muscle tissues and shifting bones physically grind against the surface of the implant. This split-screen visualization illustrates the dual threat. On the left, we see that mechanical friction. On the right, we see the second force, chemical corrosion. The human body is filled with highly saline fluids, acting as a chemical bath attacking the bare metal. Combined, they create a lethal loop. Mechanical grinding repeatedly strips away the thin rust layer, leaving raw metal exposed for corrosive particles to violently drill into. Traditional magnesium alloys cannot survive this environment. Saving the implant meant breaking this specific destructive cycle. The UniMap team bypassed temporary surface coatings entirely. They altered the atomic structure of the metal itself to create BioMag-Gd. BioMag-Gd is a specialized biomedical magnesium alloy specifically fortified with the element gadolinium. Gadolinium integrates into the magnesium to act as a microscopic internal shield. It tightens the crystal lattice structure of the metal, giving it the physical density required to resist the constant mechanical scraping of human movement. By neutralizing the friction half of the tribocorrosion loop from the inside out, the implant maintains its structural lifespan long enough for the body to heal. But mixing gadolinium into an implant carries a strict biological penalty. Adding too little leaves the metal vulnerable to decay. Conversely, adding too much makes the implant highly toxic to human cells. This graph illustrates the optimization curve, plotting structural integrity against a strict toxicity limit. The UniMap team mapped hundreds of theoretical combinations here. Through physical trials, they found the exact coordinate achieving maximum strength right before crossing the threshold of biological harm. Locking on to that single optimal peak in the data yielded the final precise formula for BioMag-Gd. The math provided the exact ratios needed to bridge the gap between a rapid chemical failure and a stable medical device. Faster, energized tone. By calculating the precise physical ratio using the optimization curve, the UniMap team neutralized the specific threat of tribocorrosion, resulting in BioMag-Gd, a stronger, safer, and highly optimized biomedical material. This engineered alloy extends the lifespan of temporary implants, saving future patients from the trauma of secondary surgeries. To learn more about this breakthrough and the researchers behind it, visit eureka2026.unimap.my.